In this video, we'll talk about the concept of equilibrium and reversible chemical reactions. Both of these will form the beginning and the introduction to Module 5, Equilibrium and Acid Reactions. We'll begin by discussing open and closed chemical systems, and that's followed by static and dynamic equilibrium, and we'll end the video by talking about the reversibility of chemical reactions. These are the syllabus learning outcomes for your own reference. What is a chemical system? Now, the word system in chemistry simply refers to the environment in which a chemical reaction occurs in. There are two different types of systems you need to know. An open system is one where matter and energy are free to move in and out of it. The word matter refers to atoms, molecules, and compounds. The second type of system is a closed system, and this is where the energy is free to move in and out, but the matter, which is atoms and molecules, cannot. So if you were to compare the two different types of systems, both systems will allow the exchange of energy in and out of the system. But only an open system will allow matter to go in and out. In a closed system, the matter will stay in the closed system, and matter that's outside the system cannot enter the system. Let's understand and reinforce this principle and concept by looking at a model or an example. Let's say you've got a pot of water with a lid over the pot. Now, this represents a closed system because the water that's in the saucepan will stay in the saucepan. And matter that's outside the saucepan, they cannot enter the pot. In contrast, we have an open system when the lid of the saucepan is removed. When that happens, matter, such as sugar and coffee, they can be freely added to the system without any hindrance. What about energy? In both systems, energy is free to go into the system and move out of it. So really, the only difference between the two systems is that in a closed system, matter is contained in the system and is not allowed to come out of it. Now, let's talk about what makes a reaction reversible. Whether or not a reaction is reversible depends on two main factors. That is the change in enthalpy, delta H, and the change in entropy, delta S. Before we discuss about reversibility, this is what you need to know about enthalpy and entropy. A negative enthalpy change is favorable as it is exothermic and releases energy. A positive enthalpy change is unfavorable as it is endothermic and requires as it absorbs energy. As for entropy, a positive entropy change is favorable as the system becomes more disordered. A negative entropy is unfavorable as the system becomes less disordered. A good analogy for this is that an entropy is really how organized and how tidy your room is. Think about when your parents ask you to tidy up your room in order to make it more organized. Tidying up, which represents a negative change in entropy, always takes more effort than making the room messier. The reason why we need to think about both enthalpy and entropy changes is because a reaction can only occur if it has a favorable enthalpy and/or a favorable entropy change. Let's explore a few possibilities of chemical reactions. A reaction can be exothermic and have a negative entropy. In this case, the reaction is driven by a favorable enthalpy change because it's exothermic. This means the reverse reaction is endothermic, requires energy, but then it will also have a positive change in entropy. In this case, the reverse reaction can occur because it is driven by a favorable entropy change. Remember that a positive entropy is a favorable phenomenon. Let's look at another scenario. You can also have a forward reaction whereby it is endothermic and have a positive entropy change. In this scenario, the forward reaction happens because it is driven by a favorable entropy change. In the reverse reaction, we'll have exothermic and a negative entropy change. In this case, the reverse reaction can also occur because it is driven by a favorable enthalpy change, because it is exothermic. What about this scenario? If you have a forward reaction that is both exothermic and has a positive change in entropy, what do you think this reaction will have? Is this reversible? You can pause the video and have a think about it. So in this case, the forward reaction is of course possible because it is driven by both a favorable enthalpy and a favorable entropy change. So again, just to remind you that exothermic is favorable and a positive change in entropy is also favorable. So the forward reaction is definitely possible. What about the reverse reaction? The reverse reaction in this case will be endothermic and has a negative entropy change. Because it has no favorable enthalpy nor entropy, the reverse reaction does not occur because there are no drivers, like we saw before in the previous two scenarios. So hopefully you can see how the enthalpy change and the entropy change can affect the reversibility of a reaction. So to summarize, we'll use a table to demonstrate the ideas again. There are two conditions under which a reversible reaction can occur. The first condition is when you have a favorable entropy change, that is a positive change in entropy, but it is endothermic. The second condition is when you have a favorable enthalpy change, that is exothermic, but you need to have a negative entropy change. Let's take a look at some examples of irreversible reactions, that is, reactions that cannot be reversed. So combustion is a very common example. Combustion reactions are always irreversible and they eventually reach what's known as a static equilibrium. We'll look at what this term means in a second. Let's use a specific example of combustion. So the complete combustion of propane in the presence of lots of oxygen produces CO2, carbon dioxide, and water as water vapor, as you can see. In this case, combustion, like you know, it's always exothermic because they release energy. Combustion is always positive in terms of entropy change because there's an increase in the number of molecules. You go from 9 gas molecules, as you can see, to a total of 14 after the reaction. So because there's a net increase in the number of molecules in the system becomes more disordered. And thus, that's why there's a positive change in entropy. As you can see from both the enthalpy and entropy, the forward reaction, that is combustion, is both enthalpically and entropically favorable. If you remember what we said earlier, if the forward reaction has both a favorable enthalpy and entropy, then the reverse reaction will have no drivers. Therefore, there will be no reverse reaction. A second example of an irreversible reaction that you need to know is photosynthesis. Again, photosynthesis, because it's irreversible, it will eventually reach what's known as a static equilibrium. If you remember from your earlier years of high school science, photosynthesis is a process used by plants to convert carbon dioxide and water into oxygen and glucose. And they use glucose as a way to derive energy and survive. The first reason why photosynthesis is an irreversible reaction is because it occurs in an open system, whereby molecules, that is matter, can enter and leave the cells in plants. And remember, a reversible reaction, it requires a closed system. The second reason is far more important, and that is photosynthesis requires enzymes, which are biological catalysts. These enzymes, they only catalyze the forward reaction, that is photosynthesis. The reverse reaction does not have any enzymes, and therefore they do not occur. In other words, in the absence of enzymes for the reverse reaction has an activation energy that is too large, causing it to be irreversible. Now, let's finally talk about equilibrium, as that's really the concept of this entire module. The word equilibrium describes a particular state of a chemical reaction. Again, there are two types of equilibrium. There's a static equilibrium, which we saw before, and that is when the reaction goes to completion. At this stage, the rate of the forward reaction and the reverse reaction are both equal to 0. In contrast, a dynamic equilibrium occurs when a reaction reaches the state whereby the rate of its forward reaction and reverse reaction are both equal but are also non-zero in value. So again, just to illustrate what static equilibrium refers to, so it is a state reached when the reaction goes to completion. So really what that means is the reaction will convert all of the reactants into the products. There will be nothing left over. That's what's known as complete reaction. So you can see when this happens, the rate of the forward reaction is 0 because there's no more reactant left. And the rate of the reverse reaction is also 0 because the products cannot be converted back into reactants, as the reaction is irreversible. So far we've looked at two examples of reactions that can reach a static equilibrium, and these are combustion and photosynthesis. Now, dynamic equilibrium is really where the module revolves around. So really this is the more important one that you need to know. And of course it's a lot more complex than the static equilibrium. So just to remind you, a dynamic equilibrium occurs when the rate of the forward reaction of a reversible reaction becomes equal to the rate of the reverse reaction. So the emphasis here being that it requires a reversible reaction. Now if you remember, reactions are only reversible if they can occur in a closed system. Let's use an example of the decomposition of calcium carbonate to demonstrate why this is a necessary requirement. So calcium carbonate, when you heat it, it will decompose to produce calcium oxide and carbon dioxide. The carbon dioxide, if it occurs in an open system whereby the container is not sealed, can freely escape the system and lose contact with the calcium oxide. In contrast, in a closed system, if we tightly seal the container, the newly produced carbon dioxide will remain in the container, and therefore it is able to react with the calcium oxide to reproduce the calcium carbonate. So in an open system, we cannot have an equilibrium. In a closed system, we can have a dynamic equilibrium. Let's look at dynamic equilibrium in a bit more detail. So when a reaction that is reversible reaches the state of dynamic equilibrium, the rate of the forward reaction, in blue, is equal to the rate of the reverse reaction. So really, at this state that's known as a dynamic equilibrium, we still have a reaction going back and forth. Every time a molecule in a reactant gets converted into the product, you have one product molecule being converted into the reactant. So the molecules are going back and forth. So there is still a microscopic change. But because the rate of the forward reaction is equal to the rate of the reverse reaction, we will see no net change in the amount of reactant and the product. So there is no macroscopic change. Another good fact to remember for a dynamic equilibrium is that at this state, the reaction has a Gibbs free energy of 0. In this module, most concepts and reactions will revolve around dynamic equilibrium, so the term equilibrium often refers to a dynamic one. When you hear the term non-equilibrium, this often refers to a static equilibrium, which is related to irreversible reactions. So keep these two things in mind when you're doing your own research and learning. We'll finish the video by looking at a simple model of dynamic equilibrium. Hopefully this will reinforce the general principles of an equilibrium system. Now suppose that I've got two containers, one with water and one without, as you can see. Now what I'm trying to do here is to transfer the water from container 1 to 2 until the water level become level. Now you must understand that this is a difficult process because if I'm not using any measuring cylinders, I can over-transfer the water, which causes the water in container 2 to become more than what I've got in container 1. Now in this model, I'm allowed to pour some water back to container 1 until I achieve the same amount in 2 containers. So after a while, if you repeat this process, you will get to a point where the water level in the 2 containers are equal. So how does this model illustrate the concept of equilibrium, that is dynamic equilibrium? So first of all, remember that a dynamic equilibrium requires a closed system. And that is demonstrated in this model because the total amount of water, which represents matter, it remains unchanged. Because yes, I am transferring between the 2 containers, the total amount of water, if you combine the 2 containers together, remains unchanged. The water transfer between the 2 containers also represents the reversibility of the reaction. And this is to emphasize that the dynamic equilibrium also requires a reaction that is reversible. Finally, the water level represents the rate of the forward and the rate of the reverse reaction. And what we are trying to achieve here is that at the very end, we are trying to make the 2 water levels equal. In other words, we are trying to make the rate of the forward reaction equal to the rate of the reverse reaction, which represents the state of equilibrium. So overall, this concept is very great in highlighting this one fact, and that is reversible reactions, it doesn't matter where they start with, they will always and eventually reach equilibrium. Of course, with any scientific models, there are also limitations. The major limitation of this model is that it doesn't demonstrate the microscopic changes that occur between the reactants and the products at equilibrium. So remember, at equilibrium, the reaction still happens, it's just that the rate of the forward reaction is equal to the rate of the reverse reaction. But this model here doesn't show that because the water remain in their respective containers.